So for the third speaker, I ask you to bend your minds, twist your perceptions, and extend your understanding of continuum robots, but this very openly, because Jessica will present her efforts on open continuum robots, because after a decade of research on continuum robots, she felt the time is right to empower the world with open hardware and open software. So Jessica, the floor is yours.
Thank you very much, Bram. Good afternoon, everyone. Happy birthday, ICRA. It's fantastic to be here. Thank you, Tamim, for putting together this fantastic program. I can say this conference is truly memorable for all of us. Today, I would like to look a little bit back into the early times of continuum robotics and give an outlook on what comes next. And looking back, I think all of us pretty much have been influenced by Victor Scheinman. He passed away about a decade ago. He's the inventor of the Stanford arm, and more importantly, probably the Puma 560 robot, which is a robot that all of us have probably learned and looked at Danavid-Hartenberg parameters and kinematics. What many people do not know is that Victor, together with Larry Leifer, in their master's work, did actually research on the very first, what is believed to be a continuum robot. And we can see it up here on the slide. It is the small robot. It's called the ORM, which is Norwegian for snake. It is composed of the 7 metal discs connected by universal joints and driven by pneumatic bellows. Didn't go any further. I guess he was way more successful with Unimation and building the Stanford and the Puma robot. However, it's still on display in the Computer History Museum in Mountain View, California. Now, the history of continuum robotics is actually quite exciting. A lot of it has also been influenced by Hirose and his work on snake robotics, and I wish I had more time to really go into it. But for those interested, I gave a keynote at ICRA in 21, which is online. I went a little bit deeper into the history, so I invite you to watch it. In preparation for this conference, I was looking at, well, which was actually the first ICRA paper on continuum robotics. And I believe it's this one. Community, call me wrong. This was published in 1990 by Greg Chirikshin and Joel Burdick. In this paper, they described a continuum robot as hyper-redundant, in fact, with very large, possibly infinite number of degrees of freedom. And he said that these manipulators are analogous in morphology to snakes, elephant trunks, and tentacles, pretty much what drives us in the soft robotics community until today. What is also really nice about this paper is that Greg started talking about representing the curvature with respect to arc lengths to describe the robot shapes using modal functions. And in Josie's great talk earlier in the session, you have also seen that this is still a way we use to describe the infinite degrees of freedom in a continuum robot body. The paper also goes on in obstacle avoiding motion plans in 2D and was really a nice early work. Another paper that I found is in 1991. This is by Susumuki, Ikura, and Tanaka. And it's a very important paper for the soft robotics community because we still see this design up until today. It's these 3 chambers that are pneumatically driven to achieve bending in 2 degrees of freedom, and then you stack multiple of these segments. They've also built a nice soft robotic hand at that time that could do pinch, pair pinch, and grasp motions. The probably most important paper for the continuum robotics community was also published at ICRA. It was the first survey paper on early continuum robot designs in '99 by Robinson and Davies. And this is the first paper that actually has continuum in the title, published at an ICRA. And they formalized the distinction between discrete, serpentine, and continuum robots, summarizing all the designs that have been out there at that time. Now, ICRA is, for many of us, often pivotal. We get some idea, make some connection with somebody, and that pretty much sets off new research. For me, such a pivotal ICRA was in 2009, when I was in Kobe. That was the time I was writing my PhD thesis, finishing off some work. And then I sat in this session and I listened to Bob Webster up here on the slide, who presented the work from Caleb Rucker, his PhD student, on concentric tube continuum robots. And I saw these robots, and before that I was doing research on medical robotics, big serial robot arms used at patients to do laser cutting of bone. But seeing these concentric tubes, super slender tentacle-like robots, I was so intrigued by the idea of building different robot embodiments that seemed to me much more suitable for medical applications and entering the human body through natural orifices or small incisions. And I was very fortunate that I became Bob Webster's first postdoc. I joined Vanderbilt University, worked very closely with Caleb Rucker and Hunter Gilbert, all now professors working on continuum robotics. And we had a lot of fun building the first teleoperated bimanual system for transnasal skull-base surgery. But I'm not going to go into too much detail on this early work. Rather, I was thinking about, well, what are all the continuum robotics, cool robotics works out there? And I wish I could fit them all on the slide, so sorry if your favorite continuum robot is not on there. These are my favorites. And what this really shows is the huge diversity of continuum robots. They exist at different scales, they exist at different lengths with very varying slenderness ratios. And there's a tremendous amount of research that went into continuum robot design in the past decades. What many often do not appreciate, if you're a continuum robotics researcher, you have to build your robot from scratch because you cannot buy one. I wish I could call a company and say, like, hey, send 3 continuum robot arms over so that we can do our research with. Now, I've been fortunate. I'm a computer scientist, and I happened to do my postdoc and my first professorship in mechanical engineering, so I always had access to great engineering students helping to build these fantastic robots. But what if you don't? So the entry barrier to start with continuum robotics research is actually really high. And that got us to create the Open Continuum Robotics project a couple of years ago. With great efforts from all the students in my lab, we created this website, and we are sharing our insights on continuum robotics and the insights of experts in the field. Leveraging all my knowledge of continuum robot course design, we write blog posts that are entry-level material for students that are early on in their robotics career, but also targeted at experts on recent research results. We publish data sets, we publish software, we publish open hardware, and that's probably most important to get those started that simply need a continuum robot to prove their algorithmic developments. Can't go into much detail, but I hope you get the point. This is all about knowledge mobilization, so I invite you to participate, contribute to this Open Continuum Robotics project in order to enable more people and a more diverse set of researchers to work on continuum robots. For the remainder of my talk, I would like to talk about the next generation of continuum robotics. Because as a continuum roboticist, I am often labeled as a medical roboticist, which I am to some extent, but continuum robotics is so much more. There are all these fundamentals that need to be investigated, and there's this whole application area that has been greatly rejected. We have been looking in medical robotics for quite some time because obviously the small scale and the slenderness helps us to enter patients on new pathways and really navigate on intricate trajectories. However, I believe there's this untapped potential in all these industrial applications. For example, non-destructive inspection of aircraft engines, investigation of or inspection of piping systems in all sorts of environments. And ultimately, continuum robots are very lightweight, so they are predestined to eventually also go to space. However, as we're going to move towards this next generation of continuum robotics, there's a whole new set of methodology that needs to be developed. And I'm going to talk about 3 exciting areas of research that are going on in my lab in the next couple minutes. The first one has to do with contact-aided navigation. So now we're building these soft, slender, compliant robots and argue it's often so safe to work in all sorts of environments. But still, for a long time, continuum roboticists have still been following the paradigm of avoiding obstacles, which makes no sense when you think about it in a way. In this line of work, which was done by my PhD student Priyanka Rao, who recently defended her thesis in collaboration with Oren Salzman at the Technion, we looked at contact-aided navigation and really shifting the paradigm to leveraging contact with the environment to gain additional motion capabilities. And here, we are actually building a very simple continuum robot that has only 3 actuation degrees of freedom, namely bending and insertion. And Priyanka and Oren helped develop this contact implicit motion planning method that gets the robot to a target pose in a cluttered environment that needs to be known. And it infers necessary contact interaction on the way without predefined contact modes, which has been quite novel in our community. And I believe that this contact-aided navigation is really what's going to push continuum robots forward. The other line of work I would like to highlight is one of the most exciting revelations I had in the past couple years. It's joint work with Tim Barfoot at the University of Toronto. Many of you know Tim as a field roboticist, and he would say, well, I would have never worked on continuum robots if I haven't met you at the Robotics Institute, which is probably true. As there, on first sight, there don't seem to be much in common between mobile robots and continuum robots. However, we found this symmetry in state estimation of continuum robots. Up there you see a mobile robot, and you see its trajectory estimation with noisy state observations. And the analogy is that for continuum robots, you can almost simply as it is, replace time with arc length and estimate the shape of a continuum robot using the same methods that have been developed for state estimation in mobile robots. We use Gaussian process regression. I won't go into much detail, but you can look at the paper from Sven Lilge, who did his PhD and is now a postdoc with Tim, continuing this line of work. You have attended the conference, so you have probably also met Spencer, who is up there on the slide, and he is taking the continuous state estimation now into 2 dimensions. So it's not only with respect to arc lengths in a static case, but in a dynamic case. So it's really a 2-dimensional state estimation problem over time and space. And this will enable dynamic estimation of smooth continuum robots shaped over time, which is important enabler for autonomous applications. And lastly, I think it is important to recognize that continuum robotics control is really far behind what we see in control in humanoid robots or serial arm robots. This is probably due to the case that the primary use case was always medicine, so we often rely on a human in the loop and teleoperation and quasi-static assumptions, robot moving really slowly. But when you move to industrial applications where time is of essence, we will really need to understand control of continuum robots better. This is 2 works from students that are also here at ICRA at 40. Up there you see Reinhard Grassmann. He's going to defend his PhD soon. And this line of work that he presented here at ICRA is truly exciting because he had the brilliant idea of using the Clark transformation to reduce the state representation for displacement-actuated continuum in soft robots. And I believe there is huge potential as this really unifies state representations for continuum robots and makes it much simpler, a much simpler control problem, hopefully. Down there you see Jimmy Shentu. He is also in my lab, a 3rd-year PhD student, and he came up with this super cool design of a universal jointed tendon-driven continuum robot, and he developed a very nice optimization scheme around a model in order to enable new helical gates. For example, this continuum robot here can propel itself through a rolling gate through a tubular structure. And lastly, I think what's going to happen next is we're probably going to look more into optimal control. This is not work by our lab, but has been some work going on in the field recently. This is from Frédéric Boyer, and they have actually found that the Kosarat rod model that we use in continuum robotics is kind of our go-to model built on continuum mechanics, can actually be formulated as a continuous time optimal control problem. And with that, I think we can bridge the gap to the more traditional robotics dynamics results and hopefully get some really exciting continuum robotics work done in the future. With that, I would like to thank all the brilliant minds behind the work I have been presenting today. It's truly them, not me, doing the work. So I'm really grateful for these tremendous and diverse set of students that I have been fortunate enough to work with. With that, once again, happy birthday, ICRA.
Thank you.
Thank you.
I see a question there.
Thank you, Jessica, for that terrific talk and fantastic perspective on the field. I was wondering if you could comment on the state and needs in perception, both proprioception and exteroperception for continuum robots.
Yeah, this is truly, I think most of us will recognize one of the most important problems because the robot bodies are very slender, very small. There's not a lot of sensors you can fit. That's why I believe the state estimation work that we're doing with Tim is really important because we can really have only a few observations along the robot body. But there's truly the need to get, I guess, better sensors integrated. We have been relying a lot on fiber break gratings to do shape sensing in a sense. You have very little feedback on the actual body of the robot once it's in the wild, so that is truly one of the big and important problems we will need to tackle and probably rely on our collective wisdom to solve this. Yeah, good point. Thank you.
Okay, thank you.